Very honored to be the first speaker, and let me start today. I want to talk about insect-scale micro-aerial robot powered by soft artificial muscles. So there are two keywords in my title, the first one being micro and the other one being soft. I want to start the first part of my talk explaining to you what are micro-robots, but the second half will be focusing on explaining what are soft robots. So first of all, when people think about robots, they usually think about tiny scale robots or large scale robots. When we think about larger scale robot, you can think about trains or airplanes. They span the scale of meters to the scale of hundreds of meters. On the other end of the spectrum, you can think about MEMS robot. They usually range from tens of microns to hundreds of microns. What I want to focus on today is talking about insect scale robots. And specifically, they range from 1 to 5 centimeters, and they weigh from 10 milligrams to 10 grams. As a quick example, when I was a graduate student at Harvard, I worked on a project called a RoboBee. And it's really inspired by bees in nature. The robot weighs about 80 milligrams and flaps its wings from 120 to 260 hertz. And if you look at the history of this project, you can see a very interesting trend. We start by implementing functions the larger scale robot can do, such as tethered takeoff or untethered hovering flight. And then we transition to think about interesting functions that are challenging, if not impossible, for larger scale robots. For example, we can teach the robot to swim in water. We can teach the robot to perch on compliant leaf, or we can teach the robot to impossibly jump off the water surface using a micro-combustion. So again, first part of the project focus on what larger scale robot can do, and later on we start to think about interesting functions that are challenging, if not impossible, for larger scale robots. So very quickly, I want to address several questions together. The first question is, why do we want to study micro-robotics? And to me, there are two reasons. The first one is, by leveraging interesting physics, we can enable interesting functions. In this case, we can teach the same robot to be able to both fly and swim. And more so, we can use micro-scale robot as a platform to investigate interesting physics at the centimeter scale. So here, by looking at how a flapping wing robot generates vortices, we can infer about the lift and drag generation mechanism of a flying insect. The second question is, what makes micro-robot unique? And the short answer is, at this scale, inertia becomes less important and surface effect become a lot more important. And as a consequence, interesting properties arise. For example, you can drop a robot from very high above, and you can see very tiny changes to its performance. And my colleague has also been able to show a jump off from the water surface, leveraging surface effects that are otherwise not useful for larger scale robots. So the third question is, okay, so micro robots are cool, but what are potential applications? The first one is, we can think about putting micro scale robot inside of cluttered spaces. In this case, we put a legged robot inside of a turbine engine. And the idea is to put cameras on board and look for cracks inside of the turbine engine. And in the longer term, we want to put a swarm of micro scale robot in very complex environment. And of course, this is a far-fetched vision. We are at least 20 to 30 years away from this, and I'll come back to addressing the challenges toward the end of my talk. So what I want to focus on today is spending a little bit of time to focus on the first two projects, which tries to show you that micro-robot, although being very tiny, can do multiple things in very complicated environment. And in the last part of my talk, I want to focus on a new type or new class of micro-scale robot that are powered by soft artificial muscles. And I want to explain to you how incorporating soft robotics in micro-scale robot can enable new functionalities. So first, let's talk about flapping wing robot. When we build flapping wing robot, most of today's flapping wing robot has 2 degrees of freedom in its motion. The wing pitch motion or the wing stroke motion is actively controlled by a actuator, whereas the wing pitch motion is passively mediated by a compliant flexure. Okay, we have capabilities of capturing thousands of flapping videos, And also, we have the capability of measuring the flow field and forces generated by the flapping wing. So here I'm showing you a particle image velocimetry experiment that we are conducting, and we are trying to analyze the leading edge and trailing edge vertices generated by the flapping wing robot. And more than that, we can construct at scale simulations, fluid mechanical simulations, that allows us to calculate the instantaneous forces. Yeah, can you see my screen? I think I may.
Now it's stopped.
Now it's stopped, right? Okay, let me stop sharing, and then I'll try to. Sorry for the technical difficulty. Let me come back to this. Let me start sharing again. Okay, so can you see my screen now?
Yes.
Okay, great. Sorry about technical difficulty. So we can also conduct computational fluid dynamic simulation that allow us to look at the forces and verticity generated by a flapping wing. So now having the tools to analyze the forces and flow field generated by a flapping wing, we are ready to answer interesting physics questions and therefore extend the functionality of microscale robots. So the question that we want to ask ourselves is there any similarity between flapping in air versus flapping in water? And if there is, can we teach a robot to both move in air and move in water? So we've come up with a project in which we want the same robot to be able to fly, to swim, and making transitions between those two environments. So very quickly, we look into biology for inspiration. Puffins are fairly amazing animals. They can fly in the sky, take a dive into water, and once they're under the water, they can modulate or change their flapping frequency so they can swim. Okay, so taking inspiration from this animal, we build robots that are similar, but having new apparatus for maintaining stability on the water surface, and also for impulsive takeoff from the water surface. So let me put everything together and show you a couple of demonstrations. So in this first video, the robot swims from the water, from the bottom of the tank. It reaches the air-water interface. And then what we do is we turn on a parallel plates that splits water into a combination of hydrogen and oxygen. And what it does is that the gas slowly pushes the fragile part of the robot out of the water surface. And you can see the robot wings slowly emerge from the water surface. Once the wings are out of the water surface, we are ready for impulsive takeoff. So now I recommend you to pay close attention to the next video because it's going to be quick. Okay, so then we are going to ignite the mixture of hydrogen and oxygen. And as you can see, a very quick combustion completes within 1/1000th of a second, which allows the robot to jump off the water surface. Okay, so once it jumps off, it cannot fly just because of all the water that's on the robot surface. What it has to do instead, it has to passively land on ground. Again, in real time, that's a very quick video. Okay, but let me show you the same video again in a slowdown time. Oops. Okay. Sorry for the for skipping the video. Let me show you. Let me try to go back and show you what's happening here. So in summary, we have created a 175 milligram robot that is capable of flying, capable of swimming, making impulsive transition from air to water and water to air, and can also passively land on ground. And you can repeat this process. So for the first time, we showed a sub-gram robot was able to move in a complicated environment and do multiple things. And that's quite a big challenge for the microscale robot in the past. In the second project, we want to show you a hybrid terrestrial aquatic microrobot. And we want to sort of continue the same thread of thought of balancing surface tension effect and inertia effect. In the first project, we spent a lot of time at using combustion techniques so that we can overcome a surface tension effect that's 10 times the robot weight. On the other end of the spectrum, as humans, we barely feel surface tension at all. And the reason is that the surface tension is much, much smaller than our own weight. Now, if we can create a robot in the center, right? If we can create a robot that weighs about 1 gram and its contact length is on the order of 10 centimeter, then surface tension and weight are on the same order. And now, if you can modulate surface tension effect, you can enable some interesting functions. So the objective of the second project is that we want to ask ourselves, how do we control the magnitude of surface tension? And if we can control surface tension, then how do we extend the locomotive capabilities of microscale robot? So for this, we have came up with a new project in which we want the same robot to be able to crawl on land on the surface of water, transition onto water, and then eventually return back onto land. So again, let me show you a video that put everything together. In this video, we show a robot starts on land, it crawls onto the water surface, now it's swimming on the water surface, and I recommend you to look at the side view of this video. Okay. Once the robot swims to this targeted site, you will see that the robot will controllably sink into water. Okay. Once it completely submerges in water, it will climb this incline to return back on land. So again, in a single video, we've shown you a microscale robot on the order of a gram being able to demonstrate fairly complicated locomotion in complex environment, which include swimming, climbing, transition, and locomotion on the surface of water. Until very recently, we start to think about new mode of locomotion, and we teach this robot to climb on vertical and inverted surfaces. And the idea of this recent project is we are using surface tension effects. That is putting a compliant pad on the robot, and we leverage capillary effect to teach the robot to climb on inverted surfaces. Again, without going into too much detail, let me just say that by using capillary effect, the robot can quite effectively climb on inverted and vertical surfaces. Although a very simple physical concept, we can see a huge performance improvement compared to the state of the art. So with that, that concludes the first two projects in which we try to demonstrate how microscale robots can do multiple things in fairly complicated environment. In the third project, I now want to change here to talk about self-actuated aerial robot. First, taking a step back, I want to say that our longer-term vision is to create a swarm of ubiquitous and multifunctional microscale robot that can perform realistic tasks in natural environment. And so far, I've shown you very capable microscale robots that are operating at high frequency and are highly precise. A lot of my colleagues in this field are solving key problems in putting new sensors and controls on board. They're also thinking about putting batteries on board. Now, I want to argue that we still are overlooking some important aspect of microscale robot, mainly being that they have very small motion and they're very difficult to make. To solve those problems, I propose we look into a different field called soft robotics, in that we know soft robot has large motion and we can make a lot of them effectively. They have new sensing and control modalities, and they also have alternative power sources such as pneumatic and chemical sources. However, the problem with soft robots is usually they are not as precise as rigid robots, and also they operate at very low frequencies. And as a consequence, the functionality of soft robots are oftentimes inferior compared to rigid robots. We propose to merge those two fields and create a new direction called hybrid soft-rigid microrobots. And the idea is that future microrobots will be powered by power-dense soft actuators, but they still have rigid appendages for effective interaction with the environment. As a quick example, I want to show you a robot that our lab has been working on in the past 3 years, in that this robot can operate at very high frequencies on the order of 400 or 500 hertz, but it's very robust against collisions, very easy to fabricate, and also it has additional functionalities such as sensing in-flight collisions and recovering from in-flight collisions. So very quickly, our robot is made of a soft dielectric elastomer actuator, and it has more traditional parts such as transmissions and wing hinges. The main insight that we have is we want to replace the state of our rigid piezoelectric actuator that has high bandwidth but small strain to a soft actuator that has reasonable bandwidth on the order of 500 Hertz, but also very large strain on the order of 12%. And to incorporate this soft actuator into a flyable robot, we really have to start with several conditions. For now, please just ignore the mathematical equations, but let's remember the conditions we have to meet, which is that the lift force of the robot has to balance its weight, the block force of the actuator has to balance the robot drag, and also the system resonance has to be matched with the inertia of the wing. If you look at those three conditions, that really imposes three constraints on the performance of the actuator. Namely, we have to look at the bandwidth, the free displacement, and the block force of the actuator. And in terms of characterizing the bandwidth, we model the system as a series RC circuit, and we show that the electrical resonance is on the order of 5 kilohertz. So the resonance of the system is really depending on the mechanical property of the actuator. And we show that through a series of experiments that the mechanical resonance of our robot is on the order of 500 Hertz. And in addition, we can characterize the block force of our actuator. We place the actuator under a force sensor, and we try to measure the block force. In this case, we show that the block force of the actuator is on the order of 0.2 Newton, which again is very big for a very tiny size of 0.1 gram. And in addition, we can also measure the free displacement of the actuator. In this case, we place a actuator under a laser vibrometer, and we measure the peak-to-peak motion. And in this case, we can see a resonance behavior. So the resonance of the actuator is on the order of 500 Hertz. Putting them together, we can compute the energy density and the power density of the actuator. And according to our first equations, as long as the power density of the actuator exceeds 200 watt per kilogram, it's possible to achieve flight. Motivated by this result, we place our actuator inside of a flapping wing robot, and we demonstrate a flapping wing motion on the order of 300 Hertz. And being very excited by this static flapping video, we demonstrated a takeoff video. In this case, this is the first liftoff of a aerial robot powered by soft actuator. And you can see the actuator behaves like muscles. We are very excited by this result, but on the other hand, as roboticists, we must admit that this is not very useful. The robot takes off and it flips over within a few seconds, and it's not very useful yet. So again, for those of you who can't see the video clearly, this is a takeoff. This is a composite image showing the same takeoff experiment. To stabilize this robot, we put two together and we use a phenomenon called precession. And the idea is that if you think about the spinning top on your desk, right, by using a fast precession, you can stabilize an unstable robot during ascending flight. And we are not going to go into the mathematical proof, but we are just going to say that in both experiments and simulation, we've been able to show passively stable ascending flight without any feedback and sensing. And that is, in our view, quite exciting because it really saves sensing and computational costs for micro-scale robots. So again, for those of you who can't see this video clearly, let me show you a composite image that shows you the same demonstration. Okay, so with one unit of this robot, we showed takeoff. With 2 units, we showed controlled hovering flight. And the ultimate question is, are soft robots controllable? Again, without going into too much detail, in fact, my student, Nemo, will be presenting his work on writing controllers for the 4-unit robot. Let me just briefly say that we have demonstrated quite good controlled hovering flight. This is a flight we have conducted last summer and it's shown in real time. This robot hovers around the set point for about 20 seconds, and you can see it's really quite stable. It stays around that set point for 20 seconds. So this is one of the best hovering flight conducted by a sub-gram aerial robot. If you look at the position error or attitude error, they're all less than 2 centimeters or 5 degrees. So again, really comparable to the state-of-the-art performance by rigid-powered microscale robot. Now thinking about new functionalities. In addition to being able to fly, visual microscale robot is robust, so they can survive collisions. And in fact, we can sense collisions by monitoring the current of those robots. We can demonstrate aggressive maneuvers. In this case, the robot can demonstrate a somersault. And well, my other student, Suhan, will present tomorrow on his work on allowing the robot to light up. Okay, so very quickly, we want to show that the robot can fly in units of 2, and we intentionally run them into a wall just to demonstrate they can survive very hard collisions. And in addition, we take inspirations from other robots very famous in MIT and demonstrate similar functions. So the Mini Cheetah is quite famous robot now in MIT. It does a lot of interesting things such as recovering from collisions or do a somersault. So the things we want to show is we ask, can our bio-inspired robot do similar things, right? So first, in terms of collision recovery, we show that while the robot is hovering, if you hit the robot is able to withstand gentle collisions and return to the hovering set point. And what's more interesting is that it can also withstand very hard collisions. In the second demo, we try to show that we can hit the robot actuators or we can hit the robot wings. Okay? And in the third demo, we want to show that if you hit the robot really hard, the robot will fall down, but then it will use the floor and bounce back to the hovering set point. Again, a good demonstration of the resilience of tiny scale robots. Okay, so for those of you who can see the demo clear or the videos clearly, let me show you composite image of the same experiment. So finally, I have about 2 or 3 minutes left. So I want to show you another thing that we are working on very recently, which is trying to demonstrate somersault. The idea is that insect can do a somersault very quickly on the order of 0.05 seconds. And in simulation, we show our robot has the control authority to do somersault. And let me show you something in real time, right? So in real time, again, because it's tiny, dynamics very fast. So let me show you the same experiment again in a slow down speed. The robot will first take off and hover around the set point for about 2 seconds. And then it will accelerate upwards. Once the robot reaches a target point, the robot will try to do a somersault, try to do a flip, and try to recover altitude. It wasn't quite able to recover before hitting the ground, but because it's robust, it sort of bounce on the floor and then return back to the hovering set point. Again, very challenging for larger scale robot to leverage the floor and do collisions. So again, in summary, the robot was able to take off, ascend, flip, recover altitude, and return back to hovering. And this is a repeatable process. We can repeat this 5 times, and the robot sees very small changes to its performance. And finally, just a hint, we have recently published a paper on electroluminescence, which is building firefly-inspired robot. Again, I think the news is coming out today at MIT, and also my student Suhan will present this work tomorrow in this symposium as well. So, in summary, we have created a soft aerial robot that is both robust and agile and capable of demonstrating unique functions. By robust, we mean the robot can fly very quickly and also recover collisions. And by agile, we mean that it can do somersault. Okay, and just very quickly about the last thing, which is we are conscious that our robot performance is still inferior compared to the state-of-the-art rigid power robot. Right? If you look at key performance metrics such as power density, lift-to-weight ratio, actuation voltage, and efficiency, there's really a very impressive benchmark being set by the piezo-driven robot that's published on the cover of Nature a couple of years back. And if you compare the performance of our robot, there's still a quite big performance gap. But I want to say that we are improving quite quickly, right? In 2021, we improved our lift-to-weight ratio by a factor of 80%, And recently, we published another paper in Advanced Material showing that we have comparable lift-to-weight ratio. Although our efficiency and actuation voltage are still worse, right, compared to the first iterations, we have been able to significantly reduce actuation voltage and improve our efficiency. So I would say that we are still making a lot of progress recently, and I'm very excited to be able to push the performance of self-actuated micro-scale robot. So with that, we also are working on multiple wing robots. We are thinking about new types of combustion-powered self-actuator, and this is in collaboration with Professor Rob Shepard at Cornell. We are thinking about flying a lot of them in a swarm, and we are thinking about multimodal locomotion. With that, let me conclude here. I want to just say that the next 10, 20 years will be a very exciting time for people who work on the topic of micro-scale robot. And I think there's a lot of interesting direction that we can push for. So let me end here. I think we have 2 or 3 minutes for taking questions. Thank you.